Hey everybody, how you doing today? I have a lesson to teach you today. This lesson's theoretically is probably pretty advanced, but at the end of trying to explain the theory of it, I'm going to show some really good technique advice on graphing transformations. So if you've been struggling with the whole XY to something or other type equation, the examples I'm going to show you at the end of the lesson might be very helpful for you. So anyway, one thing I mentioned in class today was to make sure you tried out number 9 out of the book before watching this lesson. If you've already done number 9 out of the book, go ahead and continue this lesson. If you haven't done number 9 out of the book, stop the lesson, do number 9 first, then come back and watch. All right. In that number 9, they gave you a couple of equations. F of x was this, g of x was that. And then they asked you to do some things like find, let me just grab a different color pen here. They asked you to do something like f of g of 3. And at the end, you probably got the exact, you should have gotten an answer of 3. Let's focus that a little bit. Autofocus. Maybe they asked you a backwards question, like they asked you to do g of f of 7, and when you worked it out, you got an answer of 7. Whatever number you were putting into this function, the exact same number kept coming out. The reason that happened was because f of x and g of x are inverses of each other. This is a topic that we're going to learn about in the second half of chapter 5. If you need to talk to me, you're going to have to come back later on.
Okay.
But if you know what you're doing, you just go ahead and do it.
Okay.
Sorry.
I'll just come back.
Okay. Inverses is our topic that we're going to talk about at the end of the unit. But one thing to remember with inverses is that all the x and the y coordinates are always going to be switched around. So for example, if f of 3 is equal to 5, that means that g of 5 must be equal to 3. And if you plug in 5, it is. It also works backwards. If g of 6 is equal to 7 halves, that means that f of 7 halves must be equal to 6. We tried out one more number. Let's just try out f of 1. F of 1 is 2 times 1, which is 2, minus 1, which is 1, which means, oh wait, that's kind of a silly example. I just got the same number. Let's do f of 2. If f of 2, 2 times 2 is 4, minus 1 is 3, that means that g of 3, not f of 3, g of 3 must be equal to 2, and if you work it out, I have 1/2 times 3 plus 1/2. 1/2 times 3 plus half. You got to come back later. And if you need to talk to me, you got to come back later.
Oh, I don't.
All right, then do what you need to do. 1/2 plus 1/2 is 2, so g of 3 is 2. So all of the x values of the f are the y values, or all the y values of the f are all the x values of the g. Those are inverses. What we're going to learn when we learn about inverses is that if you do f of g of x, like I did here using this f and g equation, if you're doing f of g of x with two functions that are inverses of each other, the answer will be x. At the same time, if you do g of f of x, using, once again, those two functions, you will get an answer of x. And when f of g of x is equal to x and g of f of x is equal to x, this is your evidence that two functions are inverses of each other. That leads me to how we get into the graphing. But before I go into the graphing, I got to explain this, because this is kind of confusing. Why is it that this shows that this is of an inverses? And the best way I seem to know how to explain it is that composite functions have a way of undoing each other. You had some value of x, and that applied this function here. You had then applied the inverse function to that, and the fact that they were composite functions and they were inverses of each other, the two functions basically undid themselves and they were left with x. So the first function tied the shoelaces and the second function untied the shoelaces. And that worked in both directions. Untied the shoelaces and tied the shoelaces. And we end up with the exact same thing. So composite functions have a way of undoing each other. So how does that apply to the graphing? So if I have g of x, this is an equation I have written on the whiteboard behind me. Let's say I have g of x equals 2 times f of negative parentheses x plus 3 all over 4 close parentheses minus 5. And we talked about how do we make this x. Like the point of this example is how do we know what the xy is going to turn into? Well, this is what I'm going to do. Is I'm going to change g of x. I'm going to do a couple let statements. I'm going to let g of x equals y1, and I'm going to have x be equal to x1. So that would make y1 equal to 2 times f of negative parentheses x plus 3 over 4 minus 5. So circle the function part, because this is our composite function. We have this function, 2 times some function with some stuff minus 5. This is the function stuff. And how do you figure out what the y is equal to? 2 times the function minus 5. So 2y minus 5. Oh, I made a mistake here. In my let statement, I forgot to change my x to an x1. Okay, so 2 times the function minus 5, so it becomes 2y minus 5. Then I take this stuff here that's inside the function, negative parentheses x1 plus 3 over 4, and I set that equal to some x coordinate, and then I algebraically start solving for x1. First, I'd multiply both sides by 4, so it becomes 4x equals negative parentheses x1 plus 3. Divide or multiply both sides by negative 1, so it becomes negative 4x equals x1 plus 3. And then when you subtract 3 from both sides, you end up with negative 4x minus 3 equals x1. And that's your x1 equation. So your y1 equation was 2 times some function minus 5, so 2y minus 5. And your x1 equation is negative 4x minus 3. So the composite function here, the inside function, undid itself. So when we set that inside equation equal to just some variable x, solved it for x1, that is exactly what's here. If I were to apply that to one more function problem. So in this case, it's not going to be a function. Let's have it be an x squared graph. So let's say that it was y, oh, no, I should use a g of x. So let's say it was g of x equals, let's go with negative 4, and then this parentheses, and then a negative parentheses x plus 3 over 5 quantity squared, and in front let's put a 6. So if I did what I did with this previous problem, I'd let this g of x equal my y1, and I'm going to let x equal x1. this becomes y1 equals 6 minus 4 parentheses negative parentheses x plus 3 over 5 quantity squared, or x1, excuse me. So as far as the xy goes, that inside I set equal to x, so x equals negative parentheses x1 plus 3 over 5. Algebraically solve for x. I tend to do this in 2 steps. I'd first multiply both sides by negative 5, giving me negative 5x equals x1 plus 3. Then I'd subtract 3 from both sides, so x1 ends up equaling negative 5x minus 3. I shouldn't have written this right here. Sorry about that. So my xy, the x-coordinate becomes negative 5x minus 3. The y-coordinate, I have 6 minus, I guess it's, if I handle it like before, here's the function, so it's 6 minus 4 times the function. 6 minus 4 times the function. But I normally write it as the y first, so negative 4y plus 6. But if you write it as 6 minus 4y, you could do that too. Anyway, this seems to be a pretty clear way on how to find what's going to happen with your x and y coordinate. And if you found that useful, you should use it in the future. And if you didn't find it useful, if your graphing technique is already clean as a whistle, maybe this isn't necessarily for you. I just thought it would be a good way to explain why the stuff that's on the inside of the function, algebraically always have to go with the opposite of it. Anyway, have yourselves a great day, everybody, and I will see you tomorrow. Bye-bye.